So, I think Herbert complained, because usually in a talk I do 5 to 10 minutes on this, and he said it goes by too fast, so it's going to be spread out over an hour. And I'll, all right, so I usually leave out the unipotent completion. So most people are probably familiar with unipotent completion, and this is some sort of relative version of it. But what does it do? I mean, so what does it do? It converts a discrete or profinite group, so I'll just stick with the discrete case, discrete group into a vector space. So you might say, why do you want to do that? Why would one be silly enough to do that? Well, if you start with the right ingredients, and if the group, for example, is the fundamental group of a variety, say over Q or over Z, and you take the correct data that you put in, you would expect that so anyway, the vector space is going to be an affine group, so it has a coordinate ring, that's going to be the vector space. But motives are, in some sense, I guess, they're things that give you vector spaces that have all this extra structure, like a Galois action or a mixed Todd structure, right? So in order to get some sort of motivic structure on a group, you need to do something to it. All right, and so I'll be vague about on groups. And so out of this you want periods, and I think that's the point. And so, for example, I'll talk about this in more detail later on, but if you started with, say, pi1 of p1 minus 0, 1 and infinity, you take unipotent completion. So unipotent completion is a special case. The periods, you get a multiple data values. But we want to do the same thing for modular forms. And so there you have to use relative completion.
Is there a chance you could give 5 minutes on just unipotent completion? Or
well, I'm going to do the unipotent completion of a free group in detail. So let me just, I'll do them all. It's at my next page actually, I think, yeah. Let me do this. So, so let's do relative unipotent completion, which includes unipotent completion. So let me just take so here are the inputs, and I'll have several examples. Example 1, example 2, and example 3, which I won't talk about much. I was going to, but I realized that would be saying too much. So the first thing is gamma, which is a discrete group. So think of the fundamental group of a variety, and here mainly we think of SL2Z. And F equals a field of characteristic 0. And again, here, well, we'll see in a second, R is equal to a reductive group over F. And rho, which takes gamma into the F points of this, is a Zariski dense representation. All right, so example 1, let's take, and this is the one I want to focus on because this is the relevant one, is going to be SL2Z. The second one, I'll just take Fn. This is free rank n. It's a free group. And here I could take gamma Gn, if you like. This is pi1 of mgn, with some base point, as a mapping class group. I won't talk about this anymore after this, but it should fit into the story. I mean, I'm sure it fits into the story. All right, so in every case, let me take Q, or although I could take the real or the complex numbers as well. And here I'm going to take this to be SL2 over Q. Here I'll just take it to be the trivial group. And when I take R to be trivial, I get unipotent completion, right? And then in this case here, I would take SPG over Q. So for me, G means rank G, so 2G by 2G matrices. And so, and here the representation is just the inclusion. So this looks pretty boring. Here the representation, well, this is the unique representation of the trivial group. And here, so you should think of this as somehow the automorphisms of the cohomology ring of a curve of genus G that preserves the ring. So in particular, it preserves the cup product. Yeah, let's just say H1 that preserves cup. And so there's a representation of the mapping class group, a natural one, onto SPGQ. It's the representation of this local system. It's basically the monodromy of the local system, R pi lower star of Q, where pi is the universal curve over MGN, the universal complete curve. All right, so I'm not going to talk about this one any further, but this is a special case where G equals N equals 1. All right, so now I'm going to tell you what unipotent completion looks like, or relative completion looks like, before telling you how to construct it. So what's the output? And affine F group, I'll call it G. So this is the same thing as a pro-algebraic group. So that's the same thing. As you can also write this as an inverse limit of affine algebraic groups. So 2, and I've got to say at some time the coordinate ring of G will be equal to the direct limit of the coordinate rings of the G alphas. And the second thing is a homomorphism, I'll call it rho tilde, from gamma into the F points of, yeah, that's okay. And this guy is going to be necessarily Zariski dense. And this guy has the property, put these in a bad order here. G is an extension, it's an extension of R by a pro-unipotent group. So this guy here is pro-unipotent. And so that just means, just to be totally elementary here, a unipotent subgroup is something that's isomorphic to a closed subgroup of the upper triangular unipotent matrices. Pro-unipotent means just take an inverse limit of such things. Okay? And so if this were the trivial group like it is in this column here, G would be U, and this would be unipotent. So that would be the unipotent completion. So unipotent completion is R trivial. All right, so now, and what we want, and the last thing is, oh, I didn't say something here. So we want, 4 is, we want that if we take gamma, this rho tilde here, and we map to GF, and then we map down to R of F, we get rho. And so there are many groups that might satisfy this, but we want this guy to be universal in an appropriate sense. So let me give you the construction and universal property. All right, so everybody here, I'll give two constructions, or the main one I'll give is a Tanakian one. So I'm going to let R gamma rho, so this is equal to the category of finite dimensional representations V of gamma over F that admit a filtration zero equals V0 contained in V1 contained in Vn equals V by gamma modules such that each Vj, so each graded quotient, Vj minus 1 is an R module. That means a representation of the algebraic group, and the action of gamma on it, and the gamma action is gamma. It factors through this guy here, and this guy maps into ORT. Right? So it's just, if you looked at it in terms of matrices, somehow the matrix of the representation would be look something like this. And you would, on the diagonal blocks here would tell you, whoops, these would be, here the representation would be given by a representation of R restricted to gamma, and out here you have extra jump, right? So in some sense you've got rows down, you know, some of Schur functors of rho or something like that along the diagonal. Right, so this guy is this is Tanakian, so it's the category of representations of a group. So this is easily seen to be, it's a F-linear Tanakian, closed under tensor products and so on. And you have an obvious fiber functor to vector spaces. So G, the relative completion, is just simply the what many people call, whoops, sorry, it's R gamma rho. It's just the fundamental group of this category. If you like, it's ORT, the tensor automorphisms of this guy, which takes R gamma rho into the vector spaces. Just the underlying vector space. Mm-hmm.
Excuse me, what are the morphisms in this category? Do they respect the filtration or not?
No, the filtration is not part of the information, it's just the module. Another way to say it is they're just modules that are built up by successive extensions of representations of essentially gamma that come from representations of R. Right? So if we're looking at SL2, all the graded quotients would be direct sums of symmetric powers of the fundamental representation of the group.
So it's a full subcategory of the category of gamma modules.
Sorry?
It's a full subcategory of the category of gamma modules, is that correct?
Correct. So, all right. So, and so an exercise you can construct is you've got, so this gamma rho into the representations over F of gamma, this induces gamma into GF. That's an exercise. And just for those that don't like Tanakian things, I'll sketch a more down-to-earth construction. So I resisted learning Tanakian things for several decades, much to my detriment. And I realized it would have saved me a lot of work. So the pre-Tanakian construction is this. You just look at, so you look at, you've got a collection. I'll be a little vague about this. Say G phi phi. So this is going to be G phi is an affine F group. Sorry, an affine algebraic group over F. It's going to be an extension where this is unipotent, and phi is going to be, phi takes gamma into G phi F. This is going to be rho, so these are just lifts of rho to this group here, but I want this guy here to be Zariski dense. This guy here is Zariski dense. So I look at all those Zariski dense representations here, so these would be the same, and I just take the inverse limit of them. So this is an inverse system. Right? And then, so that's an exercise, and now you just take the inverse limit. So G is just the inverse limit over all of these Zariski dense representations of G phi. So you're trying to find the largest representation of this kind, and that'll force this guy to become pro-unipotent in general. And rho tilde is just the inverse limit of the phis.
So who should be Zariski dense? Gamma in.
Sorry?
Who should be Zariski dense?
This representation here.
This horizontal arrow,
Yeah, so just look at all representations of gamma into an extension of R by a unipotent group where you have a lift of rho, which is Zariski dense, take the inverse limit. All right, so as we pointed out before, I'll just put it over here. If I take R equal to the trivial group, you get unipotent completion. And often in that case, I'll denote G will be equal to U, and I'll often denote it by gamma unipotent over F. So now I want to give I'm going to give a concrete construction of unipotent completion for a free group, and because every group is a quotient of a free group, that will give me unipotent completion of everything. That construction though is not very illuminating. It is for a free group, but it's not an illuminating construction for a general group. Okay, so example. Unipotent completion of a free group. So here gamma equals Fn, not to be confused with the field, I guess. So also write as X. So this is free of rank n. And I'm going to let V be equal to a vector space with bases, say E1. Sorry, it's F E1. Fen. So I'll take these generators here. And so the tensor algebra on V, this is the same thing as the free associative algebra generated by E1 up to En. So diamond brackets, for me, it basically means polynomials in the non-commuting indeterminants. Right, so this is free associative algebra. On the EJ. And and TV, so I can complete it in the natural topology. That's by the powers of the ideal generated by the E's, and this will be power series. So free completed. So these are power series in the non-commuting E's. Okay. And now, so the remarks here are that, so one is TV is a Hopf algebra. It's co-commutative, so Hopf algebra, and the diagonal of EJ is EJ tensor 1 plus 1 tensor EJ. So every EJ is primitive. And 2, TV hat is a complete Hopf algebra. So you might think that's a Hopf algebra, but the issue is here the diagonal goes from T hat into T hat completed tensor product with T hat. This is something defined by Quillen a long time ago. All right. And so I'm going to take I to be the augmentation ideal. So it's the ideal generated by E1, En. And so, a really silly observation is that if you look at the augmentation ideal and 1 plus the augmentation ideal, the exponential map, so this gives you an I-adic topology on T, V, and TV hat. And you can exponentiate any element that has no constant term, and you'll get something in here, and you can take the usual series for log and get an inverse, and these are inverse bijections. And so we also have the Freely algebra on V sits inside the tensor algebra on V, or if you like, the Freely algebra on the E's. This is just all the Lie words in the EJs, right? This sits inside here. It's in fact the set of elements, this is the set of primitive elements where delta of U equals U tensor 1 plus 1 tensor U. and the completion is just the same. You can also just complete everything in here. Let me get this guy here. And so, so what's the unipotent completion of a free group? Fn, so this is going to be Fn unipotent, is just going to be here. So this is, it's just the set of e to the u, such that u is an element of LV hat. And this is a group by the Baker-Campbell-Hausdorff formula, by the BCH. Right? And you have a homomorphism from, so every EJ is an element of here, so that means that the exponential of EJ is in Fn, and so we now have I'm anticipating a question here from Eve in a second, but right, so I'm going to define the homomorphism from Fn into Fn, and to be correct I really need to put the F here, and the generator xj of the free group will just go to the exponential of EJ. And that's the unipotent completion. And so the question I anticipated was, well, I've really defined, this is really the F rational points of the group. I should give you a ring, so let me give you the ring.
So may I ask a question?
Yeah.
Where is the essential that the axes are invertible?
Sorry?
You talk about a group all the time, yeah? Is it essential in this construction that the axes are invertible?
Oh, you're saying if I didn't start with a group?
Could I take a semigroup?
I'll let you figure that out.
Okay.
I've never had a need to do that, but, you know, I suspect you can do things like that. All right, so let me give you the coordinate ring, which really describes it as a group scheme or a group, an algebraic affine group. So,
is there any chance you can, so how should I think of the elements of,
sorry?
like, what does X of EJ looks like? And is there any,
What does it look? I mean, it's just the usual exponential
so
series.
it's just a series of the, so what are the elements look like? I just want to have a sense of like,
I mean, what does a general element look like?
yeah.
It looks like e to an element in the Freely algebra. I mean, this is a good construction because it's elementary and you can write it down, but it's not a good construction from another point of view. And there's something I didn't put in the notes, but maybe I'll just give you another construction over C that uses the KZ connection. And so I'll do that quickly, but let's, what are we going to say here? Oh yeah, so what's the coordinate ring of Fn? It's just equal to, I'm going to write it like this, Hom continuous of TV hat into F. So what does this mean? It's just, this has the discrete topology, so this is just the direct limit of TV, or TV hat, it doesn't matter, mod I to the n into F. And this is a Hopf algebra. It's a commutative Hopf algebra, right? And so, and then you recover the group as the spectrum here. Yeah, and why is F pro, just very briefly, why is Fn is pro-unipotent? Well, why is this true? Because it's contained inside 1 plus I mod, let me put, I've got too many F's here. Fn, say R, is going to be f intersected with 1 plus I to the r. So let's write this here. And now let's take, if I take f mod fr, fn, this will be contained inside 1 plus I mod I to the r. And this group here is unipotent. So this will be a closed subgroup of a unipotent subgroup. So each of these guys is unipotent, and f is the inverse limit of these. Right? So this is a pro-unipotent group. And so let me mention 2 examples that are important. Particularly relevant, pi 1 of p1 minus 0, 1 and infinity, and any base point, but maybe best to use a tangential one, is an f2, as we all know, and so is, in the elliptic case, you want to take the elliptic curve minus the identity x, and that's also an f2, and you can also construct the Durham version of the unipotent completion here using KZ equation, and here using KZB. And I'll mention Rome more in the connection of, so this is work of various people, but to do the algebraic Durham theory here, sort of made explicit by Rome there, in this case here. All right, so let me give you a quick. Actually, I'm going to skip the KZ equation. I can do it at the end if people want, but let me just say very quickly how to do it here. Gamma is a discrete group, and I'll assume that the dimension of H1 of gamma f is less than infinity. So this is true of every finitely generated group, and I'll just give you the coordinate ring. The coordinate ring of gamma unipotent over f is just equal to Hom continuous of the group algebra of f gamma into f, and this is just f linear maps, and by definition this is just the direct limit of Hom of f gamma mod some power of the augmentation ideal into f. Right, so that's the general construction. And so this is a Hopf algebra. And let me just state change pi 1 Durham theorem. So here we'll take M to be a C infinity manifold. I'll assume that the first Betti number so here F is going to be the real numbers, or C. And I'll take gamma equals, say, pi 1 of mx, and then the statement of the theorem is that the coordinate ring of gamma unipotent over R, or C, is just, it's equal to the set of iterated integrals of C infinity 1 forms on M. So these iterated integrals will be of the form some coefficients like, say, AJ integral omega J1, omega JR, and you want these guys here to have the property that their value on any path depends only on the homotopy class of the path. So we call these guys closed. The ones whose so for example, if M is a Riemann surface, then any iterated intervals of holomorphic one forms is closed. So I don't want to get too much into that, but I want to just say that this is somehow why iterated integrals arise naturally, because they compute unipotent completion. So let's talk about the relative case, and I want to first I can do a few generalities. So as above, we've got gamma, we've got R, we've got gamma F, R over F, and rho, right? Our basic input information. And it spits out our relative completion, G, and we've got a rho twiddle takes gamma into GF. Right? So the first generality is this, that we have this extension 1 U G R 1. So you can use Levy's theorem, the classical version, to prove that there's a splitting here. So this is split. So Levy gives a splitting. The splitting is not unique, but it's unique up to an F rational point of view. Unique up to conjugation by an element of UF. Alright, so this tells you that G is isomorphic to R semi-direct product U, which this is not canonical. And sometimes the sort of motivic theory will split out a canonical splitting in the Durham case, for example, but it requires proof. But anyway, so this implies that the Lie algebra, so this guy here, the Lie algebra of U, is a pro-nilpotent Lie algebra in the representations of R, right? Because R will act on U by conjugation, so it acts on its Lie algebra. And so to describe this guy abstractly, you just need to describe this Lie algebra as a representation and the R action on it. Right? So goal is to compute the Lie algebra U with the action of R. And every pro-unipotent group is just determined by its Lie algebra, so everything's determined by this. This doesn't determine the homomorphism of gamma into the group. All right, so the next point is just a general statement that if you have a pro-nilpotent Lie algebra, it always has a minimal presentation of the following form. You take it to Abelianization, you take you complete this Lie algebra. If this is infinite dimensional, you've got to be a little careful about how you do this, but I'll ignore that. And then it's going to be modulo an ideal, and I'll write it as MC, where C takes H2 of U into the commutator subalgebra. Whoops. You don't want any relations in the linear part because they can't be there. All right, so this guy here, and in fact it's injective. So essentially, for pro-nilpotent Lie algebras, the Lie algebra is generated by H1, and the minimal set of relations is exactly H2. It's not like discrete groups, right? And so, so we need to understand, if we're going to understand U, we need to understand H1. I'm going to write it as cohomology H2 of U and C, which are, for SL2Z, it's going to turn out we don't have to worry about this because it's not there. So, all right, so I was going, in the interest of time, I'm going to skip part. I was going to actually sketch the proof of all of this, but it's in the notes. But there's a basic result, and it follows for very soft reasons. Spencer was asking me for a proof of this the other day in a paper, and I said, don't look at the papers. This proof is far simpler. The better I understood this, the simpler the proof becomes. But anyway, the result is this. So we're going to let R, this is going to be the set of isomorphism classes of irreducible R modules. And I'm going to let, I'll write it like this, V alpha be in alpha, right? It's just choose one representation from each isomorphism class. And then the result is, maybe I'll put it on the next one. So the result is this. It says that H1 of U is isomorphic to the direct sum, this is a canonical isomorphism, alpha in R check, H1 gamma V alpha, tensor V alpha dual. And H2, there's a canonical injection from this into the direct sum over alpha of H2 gamma V alpha tensor V alpha dual. And so, and this is, these are R equivariant. So this is, these guys are naturally modules over R. Okay, so let's just assume this, it's proved in the notes actually, or sketched. So let's look at an example. It's the only example of relative completion I'm going to do, but it's the one I think people here care about, is we'll do SL2Z. And so remember here, our R is SL2 over Q. And rho is the inclusion. And you might think, oh gosh, this is the relative completion here. But it's not. And yeah. And I want to think of this as being pi 1 of the modular curve M11, if you like, analytic. Everything's over, and this is in the sense of orbifolds, with base point, say, some elliptic curve, maybe plus some other data, right? But basically the base point is the choice of an elliptic curve, and I'll set H equal H1 of this elliptic, I'll take it to be H1 of this elliptic curve, with rational coefficients, say, and yeah, maybe here for simplicity I'm going to take F to be equal to C in this. You can do it all over Q, you get the same thing, that would be the Betty story. I'm essentially doing the Hodge version here. So, and then R really I'm going to think of as SL of H. So H is the defining representation of SL2. And so what is R check? R check is just equal to, it's the set of SMH, m greater than or equal to 0. So these are the symmetric powers. And so what we get is, if we apply this over here, we get that H1 of U is equal to the direct sum, m greater than or equal to 0, H1 of SL2Z with coefficients in SMH, tensored with SMH dual, but SMH dual is isomorphic to SMH, so sometimes when you're doing Hodge theory or something like that, you have to be careful because you have weights, but let's ignore all that. So, and so also well known that the cohomology here vanishes when m is odd, so this is the direct, or when n is equal to 0, so it's the direct sum n greater than 0 of H1 SL2Z S2NH tensor S2NH. And so the SL2 action is here. This is just a dumb vector space. And now, what about H2 of U? H2 of U is equal to 0 as the virtual cohomological dimension of SL2Z is 1 because it's virtually free, as SL2Z is virtually free, meaning it has a free subgroup of finite index, right? Because all of these guys vanish. So what's this saying? This is saying there are no relations. So maybe I'll so this says that U is free. Right? So this is why this example is easy, because I don't have to deal with relations. All right, so this says that yeah, so this says that, how do I want to say this? Yeah, so this will say that U is, you look at the Freely algebra, and I'm going to take direct sum over N, H1 of SL2Z, S2NH, tensor S2NH, and I'm going to complete. And that completion is also going to turn this direct sum into a direct product. I'm going to do it over all finite dimensional nilpotent quotients which admit an action of SL2. Right? But anyway, it's this guy here. And now the next thing is, let's understand this. So we have Eichler Shimura. And so I'll write this in the most banal way, but it's H1 of SL2Z, S2NH. So I'll write it like this. So I'll write it as the modular forms of weight 2n plus 2, the holomorphic modular forms, plus the cusp forms of weight 2n plus 2 complex conjugate. Or maybe I'll write this as a Hodge structure. I prefer to think of it this way. I've got H2n plus 1, 0, plus H0 to n plus 1, and I've got an H2n plus 1 to n plus 1. So this Hodge structure here is split by Mann and Drenfeld. So this is the pure part, the intersection homology or the cuspidal cohomology. This part spanned by the Eisenstein series. So this is spanned by G2n plus 2, and these are the holomorphic cusp forms, and this is the they're just their complex conjugate, anti-holomorphic. So again, this subject presents some notational challenges. And you write all this down. So this thing's huge. The abelianization of the unipotent radical is not even finite dimensional. And it's basically, there are copies of symmetric powers of H for every eigenform, basically. Or the dual of every eigenform. So, all right, just keeping that. Yeah, so let me say something. I want to say something about the de Rham theory because we care about that. And there's so I'll be very brief here. I mean, to do justice to this would require a whole hour in itself, but let me give you some references. So, so I think the best reference is, I've forgotten the name of my own paper, so Hausdorff, I didn't look it up, theory of, I think this is what it's called, relative completion. Of modular groups. And it's published somewhere in some book, somewhere. It's on the archive, and it's within the last few years. There's an older, the general case. So I tried to make the general story as explicit as possible for affine curves in here. There's something in the, now, it's in about 1997, and it gives the general construction and proofs, does the Hodge theory. This also does the Hodge theory. And then I want to mention there's Rome, Marlowe there, who I guess this is an approximation to the Chinese pronunciation. So his thesis, which is in preparation, thesis and paper, is the Q de Rham theory. So the Q de Rham theory is not easy. And I'll try to say something about why that is not easy. And so you need this to do periods. So this here gives you Hodge, but it does not give you Q de Rham. I have some abstract argument that says you can do Q de Rham, but you can't work with it. It's impossible to work with. And so this is concrete. And I should say there's several related papers. Of Mani on iterated Shimura integrals. They've got names like that. I'll make a remark about that. All right, so there is in general there's a de Rham theorem for relative unipotent completion if the representation is the representation of a polarized variation of Hodge structure. You get the whole Hodge package, included limit mixed Hodge structures. I don't want to explain all of that, but let's just look at SL2Z. So, modular form, as cohomology class. So this is absolutely standard, but let me write it down. So let's take F to be a holomorphic modular form of level 1. Weight 2n plus 2. And I'll set omega F. I'll write this as F of tau. And I'm going to write so why do I write B and A? Because I'm a geometer, and to understand modular form, I think number theorists like generating functions, and I like to know what this means. So tau here in the upper half plane corresponds to the complex plane mod the lattice generated by this guy here. And I take the upper half plane is really the moduli space of framed lattices. So this is A and that's B. And I'll explain, I know this is probably 100 or more years old, but let me just explain. If you write down dz, and I'm thinking of H lower 1 isomorphic to H upper 1 by Poincare duality. So if you write down what dz is just A dual, because dz takes the value 1 on this, plus tau times B dual. Right? But by the Poincare dual of A is minus B plus tau A. So this guy here is really just, if I call this omega tau, this is just omega tau to the 2n. So section. All right, so this guy is omega f. So it's a holomorphic one form on the upper half plane, and it has values in S2NH. And it's gamma invariant. It's SL2Z invariant, which is what you need, and it's closed and so on. So
is there a typo? Did you switch A and B between your...
yeah, because Poincare duality, right? So A goes to A dot blank, but this is equal to B check, right?
I mean the expression of omega F. Did you switch A and B or...
It doesn't matter, it's an even power. Oh, tau, yeah, sorry, it is tau A minus B, isn't it? Okay, so typo. Thank you. All right, so, and there are various ways to see this in cohomology class, but let me jump now to step 2. So I'm trying to just illustrate how modular forms give you elements of the coordinate ring of the relative completion. So let's just fix tau 0 in the upper half plane. So this is our base point. It determines an elliptic curve and all the extra data you need to use it as a base point. And so we have pi 1, I'll be more precisely, all the fold of SL2Z, H tau 0 is isomorphic to SL2Z. And now I'm going to take modular forms F1, Fr, these are going to be holomorphic modular forms. And I'm going to take, for each one, a different copy of H. And if you think this is crazy, where are we? Must have erased it. Oh no, the top of that board up there, if you think of, let me correct a typo. There should be a dual on this, right? But here, for every, say, Hecker eigenform, you'll get its own copy of H, right? So that's what I'm doing here. I'm going to take every one of these guys has its own copy of H.
Excuse me, with pi 1 orbifold,
Yeah.
Isn't it PSL2?
No, it's an orbifold. Okay. No, it's not. Because if you think of it as a stack, you've got, if you have a universal elliptic curve, you can't have pi 1 of, say, any group. If you quotient, maybe to be more accurate, I'll put this here. If I take a point mod that, this is actually, maybe I'll put gamma here. This is actually isomorphic to gamma. And so the
it's not really in the sense, in the usual sense of orbifolds.
okay, I think there are, to me, an orbifold is a stack in the category of topological spaces.
So because it's minus one,
This thing is the homotopy quotient. It's E SL2Z crossed with H mod the diagonal action of SL2Z. It's the homotopy quotient, so its fundamental group is going to be SL2Z, not PSL2Z. So, and you need it because, for various reasons, if you kill minus the identity, you no longer have a universal elliptic curve. All right, so you have these guys here, and I'll say HJ is just going to be QAJ plus QBJ. It gets its own individual copy of H. And now I'm going to look at
So does SL2Z act on this tuple?
sorry?
SL2Z acts on each of these HAs. Yeah.
Right, so for
Is
example,
that independently or is it sort of diagonal?
sorry?
Independently or is it
Yeah,
diagonal?
if you really want to get fussy, you could take one fix. I don't like, this leads you into all kinds of problems, right? So if you look at the papers that are written, you could take this and you could sort of think of it as sort of tensored with F dual, that's its own copy, right? But this leads you to horrible formulas. What I prefer to do is suppose, see you've got
No,
meaning,
my question is you have a matrix in SL2Z.
sorry?
You have a matrix in SL2Z. And how is it acting on this tuple of modular forms? It's the same
No,
matrix in each case, but with a different tau.
See here, what's the SL2 action here? It's trivial on this vector space. It acts here. So if you take something in here, like the dual of some, Omega F dual or something, that doesn't really make sense. But take a basis and choose this, then you have this guy tensored with S2NH. So it has its own copy of S2NH. But instead I'm writing this as S2NHJ, if this was FJ, right? You're going to have, see, one thing, we think of representations, we think of there being one representation of highest weight n. But there's not. In here there's a countable number of every representation. You've got to label them all. And so typically what I do, I was going to explain over here, but I won't, is that I label them all by their highest weight vectors. And it turns out, at first you think this is, and there's a natural way to choose the highest weight, a torus and so on, because we're working with the Tate curve. And the monodromy gives you, whatever. All right, so where are we? So let's write down an iterated integral, and so we'll have omega fj will be fj tau. Tau, what did I write? It's tau a minus b. Right? We've got this guy here, and so I can look at the iterated integral of omega f1, omega fr, and it's going to have values in, and this is why I want these guys to be different, S2N1 H1 tensored with S2NR HR.
So AJ and BJ in
Thank you, AJBJ, yeah. This is not perfect either. What I do in my papers, of course, is perfect. So, all right, so what are we going to do here? So we had here's the upper half plane.
So may I rephrase my previous question? Is this tau dependent on J?
Is the what dependent on J?
The tau.
No. When you do the iterated, it depends on how you write your iterated
Yeah,
integrals,
so-
right? But here's, say, tau 0, and now we have SL2Z is going to map into G of gamma, and I want to get, sorry, G of, say, C, and I want to, given a gamma here, I want to take a function, and a function is, I can take any projection of this onto C, and I'm going to take this iterated integral, compose it with that, and I'm going to tell you its value on gamma, right? So this guy here is going to be basically a matrix entry of the, it's going to be an element of the coordinate ring. So this guy here is an element of O of G. And I've got to tell you how to evaluate it on gamma. So if I take gamma, I can take gamma of tau 0. It's the usual sort of co-cycle construction. And then there's a unique homotopy class of paths here, which I'll call C gamma. So this is unique up to homotopy. and so so this iterated integral, I'm going to write this maybe, I want to put the base point in here. So let me write, so I'm taking all these to be holomorphic, which is a little deceptive. I tau 0. And so what's I tau 0 evaluated on gamma? It's the integral of a C gamma of omega F1 omega Fr. And now to answer your question, when you do this integral, you're really integrating, you're parameterizing this path and you're taking T1 equal to or less than, using different variables here, right?
Yeah.
So when you're doing the integration, you're putting a different tau in a different T in every slot. That's okay. But I'm just describing these guys as differential forms on the upper half plane. All right. So that's this guy here. And now, sort of for motivic reasons, in the genus 1 story, here's P1C. And then we've got P1R here. So here's P1R. And in here, there's only, so here's infinity, say 0 and 1, and then P1Q sitting inside this. The only sort of base points you can use that are not in the boundary, mod P for all P, are these tangent vectors, right? So you can only use these 6 tangent vectors as base points. So when you're looking, say, the path courser here. In the genus 1 case, it's real similar, so I never know how to draw this guy. I'll draw it like this. So here's the Q disk up here, here's infinity, and this would be point corresponding to, say, I and rho. The only sensibly defined base points you can use here are plus and minus dBq. This is in the case of the module curve, right? If you want what Francis calls mixed modular modus over Z. So I want to regularize this one. And here I'm going to take, here's the imaginary axis, and you can take tau 0 here, and I want to regularize it. By the way, these are the things that Mani looked at. And I'll explain in a little bit that these are a small proportion of all the periods, all the entries of the coordinate ring here. But you can regularize this. I tau 0 of gamma will be an element of O of the Q disk polynomial in log q. So you write it as a polynomial, and it'll be something like a0q log q, sorry, a0 plus a1q log q plus and so on, and the regularized value I dq of gamma will just be a0 of 0. Right? That's how you regularize. And if this looks hokey, it's not. It's exactly how you compute limit mixed type periods of limit mixed type structures. So, all right. So let me. Yeah, I should say that after I've projected off, they look like they still look like that, I guess. So anyway, this gives you these are this will be an element. So I dq will be an element of this guy here, where we take the base point to be ddq. And then the final remark, sorry I've gone over a bit here, but let me just say, final remark is that there are lots and lots of elements of this coordinate ring that you cannot get from holomorphic forms. So the holomorphic iterated integrals, this is they form a Hopf algebra. These sit inside O of G. It doesn't matter which base point you're using. This is really small. This is much bigger. And I'll give you an example of one kind of thing that's in here that's not in here. If I take, let me just take two, just for simplicity, let me take two forms. F and G are modular forms. And let's assume that the Peterson inner product is equal to 0. So for example, I could take them to be different weights. And then I can take omega F, wedge omega bar G, and that becomes exact, and using Hodge theory I can write this as d bar of C, so this is a one form with values in the tensor product representation. And then the iterated integral, omega F, omega G bar plus C, this guy here is a closed iterated integral, and this will give you an element of O of G that you can't represent by holomorphic forms. And the bulk of the things inside here are of this form. When I say this form, they involve both holomorphic and anti-holomorphic. Alternatively, you can do the algebraic Durand theory, which requires you to use poles of higher order. You keep log poles at infinity, but you have to look at iterated integrals of the second kind, and that's Rome stuff. Okay, so I'll stop here.
Again, what the form C is for E equals to?
Yeah, so, well, let me give you a genus 1 analog. So, I mean, the question is, how do you find it? I don't know. You just go out, H2 vanishes, so the wedge of those two forms has to be exact. Hodge theory tells you can write it by something in the correct d bar or something. But the elliptic analog is this. So this is a C infinity thing. If you have an elliptic curve minus 0, and now you take dz wedge dz bar, this is equal to 0 in cohomology. So you can write it as d bar C, where this guy here is a C infinity log 1 form in F1. And you can write this guy down explicitly, and then you could look at the iterated integral dz, I'll write it like this, dz bar plus C, and that will be a closed iterated integral. This thing's closely related to Riemann's theta function. You can write it down explicitly in terms of that. but I don't know how to write these guys down for modular forms. Yeah.
So there is omega f and then omega g bar. These expressions of functions modular forms in tau and tau bar. Yeah?
Well, I'm just taking the Amega G I wrote before. It's a C infinity form. I can take
But
it.
when you put a bar, then it gets also the bar on tau.
Oh, you're saying on the everything. So the A and the B are rational, so they don't get barred. But you've got something like A plus tau B, that becomes a tau bar.
Exactly. So, but this expression is sort of separated in an expression which is in tau and an expression in tau bar.
Yeah.
Do you also have in this theory more complicated expressions which cannot be separated?
I'm not exactly sure what you mean. I mean, everything, you know, just like forms on a complex manifold are bigraded, so the iterated integrals will be, they're not exactly bigraded, but they're pretty close. If the bar construction on them, on this Durand complex is the appropriate,
Okay, maybe I tell you that.
yeah.
Any other questions?